In this paper, we delve into the intricacies of architecture-aware gradient guessing. We have significantly improved the guessing space from a quadratic to a linear scale, a crucial enhancement for neural networks with millions of parameters. We also introduced activation perturbation as a method to estimate the low-dimensional gradient, a novel approach in the field. Our research also explores partial backpropagation, a method that incorporates local architecture information into gradient guessing. This technique backpropagates a guess from the layer adjacent to the current layer. Interestingly, we found that using a single layer downstream provides the best results, a finding that could have significant implications for future research. We also investigated feature-aware gradient guessing. By unrolling stochastic gradient descent, SGD, update steps, we demonstrated that activations and gradients approximately lie in the same subspace. We introduced activation mixing as a method to generate random vectors in the same subspace as the true gradient. Our research showed that the activation subspace is often well aligned with the gradient subspace across depths, widths, and training epochs. Our results were compared to directional descent and activation perturbation baselines. The methods we proposed, such as the top-weighted approach, produced cosine similarities that were hundreds of times higher than directional descent. Furthermore, our methods were thousands of times more effective compared to directional descent in the one-step regime. Finally, we trained multi-layer perceptrons, MLPs, on various datasets. Our methods outperformed directional descent, but there was still a gap between these methods and backpropagation, which grew larger with more complex datasets. We also compared our methods against the local mixer architecture, achieving a 1.3% gain in the atom setting and a 1.4% gain in the augmentation setting. We analyzed phenomena like bias and reported the self-sharpening phenomenon. These findings highlight the improvements, modifications, and achievements of our proposed methods.